This is the first part of the lecture for Module 2 on IS688 web mining. We talk about extracting and analyzing graphs on the web. So if we want to understand or situate ourselves in the larger perspectives of the course, then we have these 5 core learning objectives. And the second one is about converting semi-structured and unstructured data into some representation that we can use to actually analyze the web. So that's one of the things that we'll talk about in this module. And then the second part is about implementing and analyzing data mining algorithms. We'll talk about this as well. So firstly, we'll focus on network structures, so taking web data and converting them into a network structure that we can use for further analysis. And then for that particular analysis, with a focus on graphs, we will explore some algorithms that allow us to extract insight from graphs that represent the web. PageRank is the main one that we'll be talking about. So from this lecture, there are 5 main learning objectives. One is being able to construct graphs from web structures, so being able to actually extract that information from structures on the web. 2 is describing ways where an adversary might try and exploit search engines or how we organize the web. 3 is talking about PageRank and how this algorithm lets us capture some idea of importance in the web graph. Building transition matrices to represent these connections between graphs, and differentiating hubs and authorities as a different way to talk about importance in graphs. So for the first one, on how we construct graphs for web structures. So as you might expect, the web and the internet in general, and the world in fact, is full of graphs and networks of different forms. So you can definitely think about the internet as network or graph in a number of different ways, from how your computer connects to your router connects to some modem, your modem connects to some ISP, and that ISP then connects to some content delivery network or larger service. Amazon also connects to that ISP, or Netflix connects to that ISP, and that's all a big network of different systems working together to provide services on the internet. Likewise, the web itself is a network of servers that host web pages. These servers are parts of domains, etc. But you can also think about networks in terms of citations. So in this visualization of papers in scientific literature, you can look at authors who cite each other or papers that cite other papers in different domains, where there's humanities that are tightly connected to the social sciences, which are themselves tightly connected to brain research, for neurology, or psychology, which are also tightly connected to medical specialties, down to infectious diseases, and so on. So you can sort of graph or track the way the web of science connects together. There's also graphs and media networks. So here, this is from about 15 or 16 years ago, where the authors of this paper looked at how political blogs linked to each other, referred to each other, which breaks down pretty clearly in the United States into liberal and conservative or left and right style parties. You can talk about graphs and author networks. So a friend of mine, Alyssa Redmiles, she writes for Scientific American, but she also has written op-eds for Wired. So you can talk about different news sources or magazines and how they're connected through authors who write for multiple sources. And of course, the graphs in social networks or social media that you may be much more familiar with. So Twitter itself has a social network, which has a lot of information about political ideology, for instance. So here on the left, we have people who retweet each other. So all of these dots represent users in Twitter, and lines between them represent whether somebody has retweeted another person. On the right, we have a similar graph, but instead of it being retweets, it's about mentions. And what we find is these different structures tell us a lot about political ideology. The retweet graph on the left very clearly separates into liberal and conservative or Democrat Republican structures, and the mentions graph is pretty different than that, suggesting that conservative or Republican users behave differently on social media this is about 10 years ago. And some of the kind of stuff that I do looks at other kinds of structures in social networks. Like this structure is a very famous one now from Kate Starbird at the University of Washington and some of her colleagues, where they looked at conversation around Black Lives Matter and then overlaid the presence of Russian information, or rather Russian Internet Research Agency quote, troll accounts, and saw that these accounts run by this agency based out of St. Petersburg actually was pretty prevalent on both sides of the discussion, both the Black Lives Matter on the left and the right, and the All Lives Matter on the right discussion, which told us something pretty important about how these disinformation campaigns operate. But that's not to say that graphs are new. In fact, graphs and the studies of graphs and networks have been around for a long time, popularized by Euler's early work in the Seven Bridges of Königsberg, which is almost 3 centuries old now, trying to identify routes that'll take you across the Sea of Königsberg without crossing the same bridge numerous times, or trying to minimize the number of times you cross the same bridge. And these kinds of problems have been around for a long time. In this particular lecture, we'll talk about a number of different kinds of graphs, specifically directed graphs and undirected graphs, and then we'll add the concept of weighting into that. But there are other kinds of graphs as well, bipartite graphs, multigraphs, etc. So the area of network sciences or graph studies is actually quite broad, and we're only taking a narrow view of it right now. So to talk about graphs, let's base this or ground this in an area that you may be pretty familiar with. So social media, popular application on the web. In Twitter, we can talk about a graph where we have 3 different people or 3 different accounts in Twitter. My account in the bottom right, the account on the left is the European Union Research Commission's account on their Center for Crisis Informatics Research, and the top right is Chato Castillo, is a well-known researcher in crisis informatics. So I can be following this European Research Commission account. This account may follow Chato Castillo, and then Chato may follow this EU account, but none of these accounts follow me. So in Twitter, what we have is what's called a directed graph, that these edges mean I follow this other account, but this other account doesn't necessarily follow me. Whereas in this top, we have these reciprocal edges where Chato follows this ERC account and the ERC follows Chato's account. And we can map this to the web as well. So on the right here, we have an article from the New York Times. And in this article, titled Washington Post Breaking News is Also Breaking, they link to a Washington Post article. So you can say here on the left, this New York Times account, or this New York Times domain, rather, has a directed edge or directed link to the Washington Post. And you could very easily imagine that the Washington Post also cites New York Times relatively frequently, and websites at NJIT may also link out to the New York Times if there's a particularly interesting or impactful article about higher education. But that's not the only kind of structure of graphs. So even going back to the social networking idea, Facebook's idea of a graph is quite different. So in Twitter, we had this idea of a directed graph, where I follow this account could follow somebody else, but just because I follow an account doesn't mean that account follows me. On Facebook, it's different. So say there's a new account, this is Lee, my wife, and there's an account about the University of Tennessee fans, or fans of the University of Tennessee's football program. And my wife and I are ostensibly friends, and my wife is friends with a number of Tennessee Volunteer fans as well. But these edges mean something different. So if my wife and I are friends, this idea of being friends on Facebook is reciprocal. I can only be a friend with somebody if they agree to be my friend. And then once that edge exists, it's bidirectional. It says something about how Facebook views the idea of connections, that 2 people who know each other in the same kind of way, which is different than Twitter. And we call this an undirected graph. So in directed graphs, we have this non-reciprocal idea that I can follow you without you following me. On Facebook, it's different, where you have this reciprocal idea, where 2 accounts are connected, and then they become peers in this relationship. So we can formalize this idea of a network by talking about a network as a collection of nodes and edges, where nodes generally represent some kind of object or entity or thing, and edges represent some kind of relationship between these things. When I talk about graphs or networks, I'll use those 2 terms interchangeably. There's no difference in my language between talking about networks and talking about graphs. A lot of it will be just contextual. As we've mentioned, networks can represent a bunch of different things. So there's the social networking aspect of friends and followers. There's the web mining aspect, or the World Wide Web, where nodes represent websites or web pages, and links or edges represent links between these websites or web pages. Communication servers, like I mentioned, so your computer has a link to your router, etc. And there are many others, from transportation networks to citation networks to biological and protein interaction networks. There's a number of different ways that you can talk about networks in a number of different fields. So from a mathematical standpoint, we can talk about graphs as being this, or a graph G is composed of these two things: V, or vertices, your nodes, and E, representing your edges. And your edges are pairs or tuples of vertices that are connected. So here V1 and V2 would be an edge. So in this case on the right, we see there's a tuple A and B that says there's an edge between A and B, a tuple BC that says there's an undirected edge between B and C, ED, and so on. And generally this set of edges is a subset of the Cartesian product of your vertices. And then the order of these represents whether you're talking about a directed or undirected graph. So here we have an undirected graph where A and B have an edge. If we wanted to make this a directed graph, then this tuple AB would say there is a graph, or an edge rather, from node A to node B. And if we want to represent a reciprocal directed edge from B to A, we would flip the order or add a new tuple with the order B, comma A. When we talk about graphs or networks and what these nodes represent, you should generally be, when you're creating your own graphs, which I have asked you to do for the Module 2 assignment, note that your nodes are generally the same type of thing. So that means that connections between these two nodes also should represent the same kind of relationship. Now, that doesn't always hold, and it certainly is a rule that you can bend or break depending on your context. But in general, at least early on, you should be thinking about, well, all the nodes in our graph represent social media accounts, and all of the links or edges between these accounts represent friend relationships or following relationships or something like that. Now, even with Twitter, we see this isn't quite true, because you can have follower accounts, but you can have follower relationships, but you can also have retweet relationships. So does that mean that you represent those in the same graph, or do you represent following graphs and retweet graphs using two separate structures? That depends on your context. So before we move on, let's give you some more vocabulary about networks. So if there's an edge between A and B, we call A and B neighbors. If F, this node F, has no incident edges, that means that there are no edges connected to it or no tuples in our set E, then we say F has no neighbors and is what we call a singleton. And we can also allow for edges between a node and itself, and we call these loops or self loops, which you can definitely have, especially now on Twitter. You can retweet yourself, these kinds of relationships that are maybe not as common, but definitely possible. So we can also talk about the idea of weights or importance, or this kind of way to differentiate edges in our graphs by talking about weighted graphs. So what we've been talking about so far has been unweighted graphs, where if we have some edge, that is a pair of vertices, then in the unweighted case, all edges mean the same thing. But does that really ring true for all cases? Ostensibly, my wife and I are closer in relationship than my wife and the University of Tennessee. So we can capture this by talking about weights or weighted edges. We add some numeric weight to these edge links. So for example here, my wife and I may have an edge weight of 10, and my wife and the University of Tennessee, she maybe sometimes likes UT more than she likes me, would have a much higher edge weight. And what these edge weights mean, again, is contextual. And in fact, there's a whole area of study about what edge weights mean and the importance of lowly weight or small weighted edges and edges that have high weights. So what these edges mean can mean, or what the weights of these edges mean, again, like I said, is contextual. In the context of the web graph, it might be the number of links between two domains. So the New York Times almost certainly links to the Washington Post way more than it links to Fox News or to Breitbart based on ideological positioning. But it could also be duration. So if you talk about social networks, then how long two people have been friends may tell you something about the weight of your edge. Or if you're talking about geographic networks or communication networks, maybe weight means proximity. So we want to send messages across communication links between nodes that are close to each other rather than nodes that are very far away to reduce latency or something like that. So how do we represent and store graphs? So now that we've talked about this idea of having a graph that is composed of vertices and edges, how do we represent this? Because we're going to have to do some processing here. So as I mentioned, we have our edges, which are sets of tuples of vertices. Well, the most straightforward way is to just talk about this in terms of edge lists. Just basically, you could think of it as a CSV or an Excel spreadsheet or just a text file. It has a list of all the edges in the graph. And nicely, you can say, well, if we have this edge list, assuming that there is at least one edge for every node in our graph, then this edge list is all you need to characterize the full graph. Though there are some constraints here about, well, what happens with singletons that have no edges, things to pay attention to. So we would just have a list, AB, BC, AC, and so on, in a document that represents all of these edges. Another very common representation for graphs is called the adjacency matrix that lets us talk about graphs in terms of how many nodes there are. So we have a number of nodes in, which is the size of our set of vertices. And our matrix A is this n by n matrix called the adjacency matrix, where the ijth value in this adjacency matrix represents whether there is a connection between the ith node and the jth node. And whether this network is directed or not tells you whether this adjacency matrix is going to be symmetric. So if it's undirected, then if there's a 1 between B and A, there must also be a 1 between A and B. But if it's undirected, we have this triangular matrix. If it's a directed graph, then just because A is connected to B doesn't mean B is connected to C, or B is connected to A rather. So here in this graph or in this adjacency matrix on the right, this is an undirected graph. You can see that from the triangular nature of this adjacency matrix. This matrix actually has a number of different uses, both in terms of characterizing graphs, but also mathematically it has a lot of interesting properties and features, one of which we'll talk about when we talk about the stochastic adjacency matrix and modeling transitions among websites. There are certainly other options for representing graphs. There are adjacency lists, which is similar to an edge list, but we start off with the node and all the neighbors of that node, which lets us to deal with cases where we have singletons. There's specific markup languages for representing graphs, like GraphML or GML or GEXF, and there are a number of others as well. So there's a library or a number of different libraries for characterizing graphs that you can work with. So NetworkX is a really popular one for Python. There's ones for R. There are ones for, and like I said, numerous other languages. And you could just, if you want to look at all the different kinds of, or a number of different kinds of representations of graphs, you can check out NetworkX's list of reading and writing graphs. So what does this have to do with the web, you may ask? So if we look at the learning objectives, what we're going to talk about now are two specific ones about how somebody might try and explore search engines and how a particular algorithm called PageRank allows us to use networks to capture importance of web pages. And we'll motivate this by a particular question of trying to understand how we organize information on the web that makes it available for people to find quickly and easily. Back in the early days of the web, this was done by what are called curated web directories. So you may see or have heard of the Best of the Web, which is an existing directory, a manually constructed directory of web pages that's been around for a long time now, 26, 27 years, something like that. But the issue with these kinds of approaches, where we build these web directories through manual curation, is that they're very slow, time intensive, with the number of new websites that are added to the web daily. This is actually pretty much intractable and really doesn't work well for the international or transnational internet that we now have, where we have to deal with websites in many different languages, these kinds of questions. So the next step was search engines based on techniques of information retrieval. Maybe you've heard of Ask Jeeves from ages ago. Now, this has led to growth in an area of research called information retrieval. The general idea here is if you provide some query, like say you want to find messages about or websites about Amanda Gorman, the Youth Poet Laureate in the United States, you might search for websites that contain her name. Naturally, you might find the Wikipedia page for her, or you may find her website. But if you were only looking for pages that had the words Amanda and Gorman in it, you might also find something like web stores that share t-shirts. Now the reason for this is if we're allowing websites to basically say, oh, I'm relevant to your particular query because I have a bunch of your keywords in my page, then what we do is we leave ourselves open to exploitation, because some adversary can say, well, I don't actually care about how you got to my page, whether you're actually searching for Amanda Gorman. Really, I'm trying to make money. I'm incentivized to get people to my page to buy my t-shirts, regardless of what is on my t-shirt. So this approach really damaged the early versions of search engine technology, because it was very easy for somebody to take a particularly popular keyword, shove that keyword into their web page. Maybe they'll make the keyword invisible or change the color of the text to prevent it from showing up from somebody looking at the page, so the user doesn't immediately suspect they've been duped to get in here, and really pollute the search results for a lot of the early search engines. And there's a lot more sophisticated ways of doing this. So maybe you've seen people putting meta tags into their tops of their web pages that have a lot of keywords, so looking for popular keywords or keywords about the current president or about the Olympics or something, even for websites that have nothing to do with those topics, purely to drive traffic. The book makes kind of a claim about this, that people talk about this or have tried to disguise this kind of behavior using the more innocuous term of search engine optimization, or SEO. It's a pretty popular term and has whole industries and positions at companies devoted to this. But the idea is there's a lot of opportunity here for people to spam these kinds of search engine results through content spam, stuffing keywords that they're hidden or in meta tags, and a number of other ways. There's a whole website on Wikipedia, or a whole page on Wikipedia about all the different ways that you can try and exploit these things. So if we go back to the motivating question about how do we organize the web despite these issues, really this breaks down into two problems. One is finding relevant pages. So this is looking for pages that have the keywords I'm searching for, which can be done using standard kind of information retrieval approaches that just do keyword matching. But also we want to look for pages that are trustworthy, pages that are not owned or driven by adversaries who are trying to get you there on sort of false pretenses. So how do we find pages that do both of these things? The answer to this really is the application of networks, where we make a couple of heuristic assessments here, that pages that are not linked to, pages that don't have very many incoming links from other pages, are likely to be less trustworthy, less interesting, lower quality pages. Whereas pages that have a lot of these links coming into them and are grouped in with a number of other pages are likely more important and likely to be of similar topic. And we'll talk about what that means here, or the relevance of the topic aspect in a bit. So if we want to look for pages that are important, we can try and find pages that are embedded in these dense clusters, because things that are well connected, pages that are well connected to the rest of the space, are more important. And we can think about this in terms of, from a graphical perspective, if some web surfer is just randomly clicking through links on pages, they're likely to end up in these places, which makes them more interesting from an informational perspective. So how might we do this? Well, a naive solution may be to rank these pages based on the incoming links, the number of incoming links. So pages that have many incoming links are, in some sense, more important. And this actually is a well-known centrality metric in network science called degree centrality, where here in this particular sense, we'll say it's in degree centrality. So we'll talk about this as a directed graph, and the incoming links are, the number of incoming links a particular node has is its in degree. But the issue is here, if we are having to deal with an adversary, especially in today's world where cloud computing is so easy, an adversary can create a large number of fake servers, and all of them have links that point to the t-shirt shop. They're the t-shirt website that he's trying to get you to go to. So just allowing or just ranking by incoming link still leaves us open to exploitation here. This is what's called link spamming. So how do we deal with this? How do we find important pages that are robust to the keyword manipulation aspects that we talked about, and robust to this link manipulation idea? Well, fortunately, in the late 90s, Larry Page and Sergey Brin created the PageRank algorithm, which really was the foundation for Google and Google's search engine. Yeah, now the idea with PageRank is that if you're given a graph, we want to not just look at the in degree, but we want to have weights for these pages that are based not just on how many people are connected to us, but how many people are connected to the pages that are connected to us. So if we scale this out and say, well, what we really care about are links from pages that are themselves well connected. So the summation for PageRank here is the size or the weight of a given node, how important it is for, or valuable it is for our ranking, is proportional to the sum of all the node sizes for all nodes that point to it. So if we look at this from the standpoint of the adversary can have all of these pages that are linked to his website or t-shirt page that he's trying to get you to go to, but it's likely that these fake nodes aren't going to have any incoming links, that they're not very interesting, they're not very important, so their weights overall should be relatively small if we're trying to say, look for pages that are linked to by other pages that we care about. So if we go back to thinking about the web as a graph, where nodes represent pages, websites in the internet, or websites in the web, and the links from website or web page to web page are directed edges in our network, then what we have is a nice intuition that pages vote on each other, vote on how important other pages are by linking to those other pages. So websites that have just a few links coming into them are maybe less important than websites that have many links going into them. And this makes intuitive sense because you could imagine I create some personal web page for me. Nobody really knows who I am, so no one links to it. But Wikipedia has many pages that link to it. And as a result, we'd make some assessment that Wikipedia as a website is more important than my personal website. So yeah, the idea here is pages with more end links are more important. But to deal with the adversary perspective, then we have an addendum. That it's not just the in degree, the links, the number of links that come in, but really how important are the sources of those links? Are important pages linking to me? And then we can see there's a clear difference. So if my personal page is linked to by Wikipedia and by Amazon, well, that means that my personal page is maybe much more important or much more well embedded in the web than some other random website that has a bunch of links from other no-name websites. Which leaves us with this sort of recursive definition that particular website's PageRank or importance is based on the PageRank or importance of other sites that are in fact linked to it. So we can define this mathematically using a notation where a PageRank for a given node in our graph has some score R sub j for a given page j, And this rank can be distributed across all of its outgoing links. So this is the voting aspect. If I have some particular importance value or rank or score, then when I link to other pages in the web, I get to distribute my importance across all the websites that I link to. So we have this relatively straightforward equation where the particular rank for a given page is the sum of all of the other pages that have linked to it. For each of those other pages, their weight divided by all their out degrees. So all the other links that they connect to, distributed evenly across all of their links. Let's sum up just the ones that point to me. And this actually can be calculated relatively easily in distributed fashion using message passing. But I'll give you some intuition for how this works. So say we have a graph like this, where at first all nodes have the same weight. You take one step forward, and all of these nodes down at the bottom that have now a score of 0, well, they have no incoming links, but they link to a number of other pages. So those pages get slightly more weight based on who's linking to them. And if we take one step more through the recursive or through the iterative definition of PageRank, we get slightly larger nodes based on all these other nodes that are connected to them. So first we see this blue node is in fact linked to by the most other pages. It has an in degree of 1, 2, 3, 4, 5, 6, 7. But interestingly, this orange node also has a really high PageRank because this blue node that has such a large importance factor or PageRank here is only linking to one other node. So all of its vote share goes to this one additional node. Whereas like this blue node in the middle spreads out its authority or importance across a number of other nodes. So you could very easily imagine that this blue node is YouTube, this yellow node is Amazon. Lots of people visit YouTube, many people visit Amazon. These sort of in-between nodes are social media sites, and these bottom nodes are sort of less important random sites that no one really links to. An issue with this sort of evaluation, though, is that it can be slow for really large graphs. And we're very much in that space for the World Wide Web because we're talking about billions of pages. So we need an alternative method for dealing with PageRank or calculating PageRank, which leads us back to our PageRank definition, where we can take this adjacency matrix that we saw before. We'll make a slight modification to focus on an adjacency matrix for this directed graph, where we see the column A tells us what nodes A points to B, and A points to D. The column B is connected to C, the column C shows C is connected to A, and so on. And we'll make one more modification and convert this adjacency matrix A to the stochastic adjacency matrix M, where every edge weight in our matrix is divided by the degree of the source node. We see for node A, it has an out degree of 2, so each one of those two edges has an evenly split edge weight. So each one of those edge weights is 1/2, whereas vertices B, C, and D only have an out degree of 1, so their edge weight is 1. Now, an important thing to note here is that the sum of all these columns should equal 1. As mentioned or as described by construction, this matrix tells us the full distributed weights for all the out degrees for these nodes. So then we can take the PageRank equation that we showed you before, and we can rewrite this using matrix notation. And we see this rank vector, this rank column vector R actually equals this transition matrix, stochastic adjacency matrix M, times this column vector R. Now, if you are sufficiently familiar with your linear algebra, you could see that this vector R actually is an eigenvector of this transition matrix M. So we have this lambda R equals M times R, where lambda here in this particular case is 1, which means that we can evaluate these PageRank scores by looking for the largest eigenvector of M. And we can do this using a trick from linear algebra called power iteration, where we initialize our vector first with 1 over n for every node in our graph. So what this says is we'll start off evenly distributing our page ranks across all nodes in our graph. And then we'll take our transition matrix M, multiply it by this column vector R, and then we will iterate on this. So once we have a new value of R, we'll then multiply M by that, and then keep doing that until we reach some stopping point in our iteration, some point of convergence, or where the delta between our current R and the previous column vector rank is less than some value. And now we have a good estimate for the eigenvector, the largest eigenvector of this transition matrix M. And that, just from that vector, we can read off the page ranks of the nodes in our graph. And this works well for graphs that are strongly connected. What this means is for graphs where you can get to any node from any other node, that there exists at least one path from any page to any other page in the network, then this works well. And what happens is this eigenvector, or the weights in this eigenvector, correspond to the likelihood of some random walk through this graph showing up or landing on one of these pages. That the higher this eigenvector, or the higher this eigenvector's value is for a given node, the more likely you are to just randomly land on that page if you are doing a random walk through the graph. But that's not really how the internet's constructed, right? Or the web is constructed. There are dead ends and neighborhoods in the graph that once you're in, you can't get out of. The book refers to these as dead ends and spider traps. So we have to make extensions to PageRank to deal with these irregular structures, either through transporting or random restarts, these kinds of things. The book has more insight into this. So what I've given you is a general idea of how PageRank works. So now what we want to do is talk about how we integrate that with the information retrieval methods that we talked about before. So if we go back to this query idea where we have a query for Amanda Gorman, this Wikipedia page has the search terms in it, Amanda Gorman, so does her personal page, but also so does this t-shirt sales page. So we can't change that. We can't change that somebody has embedded all these references to Amanda Gorman in their page. But what we can do is integrate this PageRank idea, and then rather than showing here are all the pages that contain these keywords and how many times they contain these keywords, we can now re-rank these pages based on their PageRank. So pages that have large values of R, or large PageRank values, are shown to users first. So we get the largest R, maybe this Wikipedia page. The next largest R is Amanda Gorman's personal page. Maybe there are many pages down between that, and this t-shirt page that is using some strange or illegitimate way to drive traffic has some very small R. This is not a very trustworthy page, so it is far down in the page results. But even if we deal with issues of spider traps and dead ends and all these things, and integrate that PageRank approach with the information retrieval approach I just showed you, there's still some open problems here. First is that PageRank really only gives us generic popularity, so there's no real way to differentiate between pages that are about animals versus pages that are about science versus pages that are about medicine. It really only gives us one measure of importance, even though two pages that might have a lot of high quality information in them may have different kinds of information, not just by topic, but are built around different things. I'll have an example of that in a second. And there's still opportunity for manipulation, though generally that's harder. I'm not going to go deeply into more ways that PageRank can be manipulated. Just know that as long as there's financial incentive to manipulate search engines, as there always is, then there's still going to be opportunity in people who are trying to exploit them. For the first one, though, about measures of generic popularity. So you could very easily imagine if you're trying to look for the query Jaguar. So Amanda Gorman is a very clear, almost singular identity. She's the Youth Poet Laureate, so maybe there are other Amanda Gormans, but they're not very popular. In this case, if you're going to search for the query term Jaguar, well, there are many different contexts where Jaguar makes sense. It could be the automobile manufacturer. It could be Jaguar the cat, or it could be, to date myself a little bit, it could be a version of OS 10, which is actually the example from the book. How do we separate PageRanks for these different topics? And is there a way to do that? And then here in the middle one about there's only one measure of importance. So if you think about what is the meaning of Wikipedia, how important should it be? Well, it's clearly one important website, but it's qualitatively different than if we're trying to understand something about the stock market today. So Wikipedia will probably tell us a lot about how stocks work, or historical trends about the stock market. But if you're trying to understand something about a very particular niche idea, or get new insight from how the S&P 500 is doing today, right this moment, Wikipedia is not going to be a good source for that. So there are two different kinds of pages here that both are important in a key way, but are still different. So there are solutions to each one of these. For the idea of measuring, or the issue of measuring generic popularity, there are extensions to PageRank that are broken down by topic. So one is this idea of building separate PageRanks for all the different topics that we have. This is actually the Mozilla directory approach, but DMOZ doesn't exist anymore, as one might expect. So other kinds of approaches, rather than building topic-specific PageRanks, actually try and build PageRanks that are user contextual. So looking at your particular history and then trying to evaluate which PageRanks are good for your particular interests. And you could imagine this is why browsing histories and user behaviors online have so much value, is because they allow products like Google search engine to be better at trying to identify what your particular interests are. For this issue of having only one measure of importance, so this has been extended into separating different kinds of pages. That pages that have high PageRank could have different roles in the internet. Specifically, we'll talk about roles in terms of hubs and authorities, where authorities are generally topic-specific sources, where people go spend a lot of time on the page. They don't generally then leave to a number of other pages. These pages provide sort of a terminal node in the path of information about a particular topic, which is separate from this idea of hubs, or aggregators that link you to a number of different authorities. So I would say Wikipedia is probably a good example of a hub. You go to a particular Wikipedia page, you look at the references on the bottom, and then you share or spread out from Wikipedia to other domains by looking at those references. Whereas if you're trying to understand something about the stock market, maybe you go to MarketWatch and you bounce around a lot within the MarketWatch webpage or website, but are less likely to leave to go to other sites. So this separation into hubs and authorities is actually what the hits algorithm allows us to do. I won't go deeply into this other than to have differentiated what hubs and authorities are. The book has a good explanation of the hits algorithm if you want to learn more. But that rounds us off for the lecture today on thinking about the web in terms of graph structures and what we can learn. So we can now talk about being able to extract graph structures from the web, looking at links as edges between pages. We have talked about ways that people have tried to exploit search engines for financial gain, which has incentivized us to rely on this graph structure and the PageRank algorithm to evaluate importance and trustworthiness of pages in the web. We've talked about how we can extract a transition matrix, this matrix M, the stochastic adjacency matrix, that tells us something about how likely it is you may move across the pages in the internet. And then we've talked about how PageRank really only captures one kind of importance, but there are other kinds of importance that we can capture with this idea of hubs and authorities. So that rounds, like I said, that rounds us out for discussion of Chapter 5. Chapter 10 and social networks on the web we'll talk about next week. If you have any questions about any of this material so far, you can post it in the Module 2 discussion forum on Canvas.